Constantino. Okay. And that was Schmetnas, the Moldau by Beatrix Schmetna. That. by Vivaldi. We're getting close to the end of summer. So, enjoy. Oh, I think I'm out of time.
Hey, Kim, we're at 7:30. Thank you
Yeah.
ever so much. As usual, we really appreciated that. That was beautiful. And I think it is now time to start our September meeting. Thank all of you for joining us. This is the September meeting of the Orange County Astronomers. I'm your current president. My name is Barbara Toy, if you haven't caught on to that yet. And before we get on with our regular program, I would like to make a couple of announcements for those who may not have been following the recent news. There is a big fire near Hemet. It is unfortunately not all that far from our dark site, which is near the town of Anza. As of this morning, for anybody who may be thinking of going out there, the main highway in 371 was closed, and we don't know if and when it's going to be reopened. There have been evacuation orders in effect in the area. That changes as the firefighters' needs change. If you are thinking at all about going out there, please check with the CAL FIRE website and any other sources of information you can find about what the current status is to even determine whether you can go out there. If you think that you may be wanting to observe out there, please keep in mind that smoke is not really desirable when you're talking about optical equipment. And it also kind of impairs the view of the sky. Another aspect of what has been going on recently, we are in the fringes of a hurricane, and there has been a lot of thunderstorm activity that can affect the quality of the roads. So again, when we finally are able to go out there safely due to the fire, you are thinking of doing that, please double check to be sure that the roads are going to be in a condition that your car can handle. And a last point on the Chapman meetings, I know several people have asked about what's going on. We are in contact, or I should say Charlie, who has been really doing the major work on this, has been in contact with Chapman University. And we are in the process of finalizing the paperwork that's needed before we can start the in-person meetings again. So please keep an eye on the website and on the email groups, and we will keep you advised when we know when we are actually going to be able to restart the in-person meetings. And with that, I would like to welcome my colleague, Helen, who has agreed to do the announcements for tonight with me chipping in as appropriate. Take it away, Helen Mahoney.
Thank you very much, Barbara. I'm Helen Mahoney, board member and former president. And tonight, welcome to the September 9th meeting. I want to welcome our new members. It's wonderful that you folks have joined, and there's a lot of wonderful activities that you'll be able to enjoy, and you'll be seeing, you saw those in the slides, the pre-meeting slides, and I hope you have a wonderful membership. Star parties, the in-town star parties are still up in the air. They might start soon. Please continue to check our website for that. Anza Star Party, September 24th. Hopefully by then we will have the fires gone and the hurricane out of the way. Special interest groups, the September Astrophysics group is going to meet at the Heritage Museum. The Astro Imagers they might be meeting somewhere on ground soon, but stay tuned for that. The beginners class is online October 7th, and our board meeting is this coming Sunday, September 11th. For outreach, the school year.
Helen, I think you cut out.
Yeah, it says the host muted me, so I'm back, hopefully. Can you hear me now? Okay. Did I say something wrong? The school year has started, and so Cecilia Caballero, our outreach coordinator, is looking for volunteers because we will be having a lot of requests for outreach events. I will step in for Galileo and tell you that it is a waxing gibbous moon tonight. May not be able to see it with all the clouds, but it's almost full, 99% illuminated. Our Adoptoscope program, our former Lonerscope program, is now an Adoptoscope program. We have a lot of wonderful telescopes that you can get to preview, and if you like it, you can. Some are free, some you pay a small amount to keep. And as John Hoot, our Adoptoscope coordinator, says, if it's like a puppy, if it doesn't work out, you can return it. So check the website for that. Our Serious Astronomer is our newsletter, and if you have anything that you'd like to publish, send it to David Fisher. Everybody gets the newsletter by mail unless you opt out. If you want to save resources, you can contact Charlie at charlie@ocastronomers.org, and let him know that you just want the version that comes with the website, which is in color. Please, if you're out at ANSA, do some weed clearance. It'll help in case of fires like this to prevent these things from spreading. Keep your pads and observatory clean. Next meeting is October 14th. And then tonight we've got What's Up with the wonderful John Garrett, and our featured speaker tonight, Dr. Nicola Tomasetti. And I really appreciate him getting, I think it's very early in the morning where he is, and I really appreciate him getting up and joining us. And so now we really want to introduce John Garrett for the What's Up. Thanks.
Well, hi, good evening. Is everyone seeing my screen? I can't tell if we're seeing it.
Yes, all good, okay. John.
Thank you so much. Thanks again for letting me do the What's Up tonight. It's been a challenging month, I'll say, as far as getting outside and getting to dark locations, which I failed to do mainly because the weekends were filled with monsoon storms, and then it got super hot. I'm okay with the heat, but the telescopes aren't good with the heat, so it got a little hard to set up. But I did get one real benefit because of the fires that we've been having. The smoke has been coming my way for a couple days, and 2 nights ago I was able to get a photograph of the moon with a telephoto lens. And so this isn't an eclipsed moon, it's actually a moon shining through the fire smoke of our ongoing brush fire. And as you look at it, you can tell a couple things. Beautiful coloring the fire can give an object like the moon, but also that it's getting close to full moon, which is this weekend. So full moon will happen, and we'll get over this full moon weekend, and then we'll have a couple weeks ahead of us of good dark sky observing. But speaking of red objects, the Mars, the famous red planet, is starting to come back. I've been seeing it showing up in the morning sky, and every year or every 2 years when we pass Mars, I say to myself, this is the year I'm going to try to do some serious planetary imaging, and I still haven't. But once again, this is time is coming up, so you might want to start planning for Mars if you need, like me, to learn to refine your planetary imaging. But this is one I took 2 years ago. And just to show you where the planets are right now, here's a simplified drawing of our solar system, and Earth is about making that transition from the August into September, which will put it into the autumn time for the northern hemisphere. And of course, our orbit is elliptical. Nothing's really to scale here. And Mars's orbit is also elliptical, approximately like this. And this is about where Mars is relative to Earth. And so Earth is now going to be overtaking Mars. And by December, Earth will be a parallel with Mars, and that'll be Mars's opposition. But if you consider the orbits, the month leading up to Mars may be just as good as the month when Mars is at opposition as far as for imaging. And so you never know what the weather's going to be, so it's never too early to start planning for Mars when it shows up. Using this diagram, and it's really getting not to scale now, Saturn would be in this direction from where we are, as shown in this diagram. And I do have a photo that can show where Saturn is. Here's the constellation Capricornus. I photographed this a couple of years ago when Saturn and Jupiter were close together in the sky, and you see them down in the lower right. But now Saturn's made its way to up there in Capricorn. And so it's come some ways. And so it's out in the evening and still out, rather late in the evening. So it's a good time to still see Saturn, though it is getting smaller because we are putting some distance between us and Saturn. And so adding to these planets, Neptune is going to be at opposition. And again, my scale is way off now, but Neptune will be in that direction, and it's at opposition just next weekend on the 16th. And then Jupiter comes to opposition at the end of the month. And by the way, opposition means Earth passes it on the inside track so that the planet is closest to us, and that's going to be our best time to see it this particular year. and Jupiter is at opposition the 26th. And now I'm trying to illustrate Jupiter, Neptune, and Saturn approximately the sizes they may appear in a telescope where you're using the same magnification on each. I think Neptune would be a little bit smaller, but I wanted to make sure that you could see it in this diagram. And then Uranus will be out in this direction. And now I'm going to move Mars out with the other planets, kind of making a partial Aristotelian view of our solar system. And so here's where these objects will be. And this area of the sky that I've illuminated is what we see in the evening at sunset and shortly after sunset. That's our field of view. And so we'll see Saturn will be up pretty high in the east when it gets dark. And Jupiter and Neptune will be just rising. And then as the Earth rotates around by midnight, this is our field of view. And Jupiter, of course, will be up all night. And Saturn will be setting by then, or getting close to setting. And then Mars and Uranus will be getting fairly high in the sky. And then as the morning, those two get even higher in the sky. So if you're an early morning imager, those would be good objects to start on. But the others you can start on in the early evening, and they're great views for telescopes. And I was hoping to find a comet. There's a few out, but most of them are pretty faint, above magnitude 11. And the only one I was optimistic about was Comet C 2017. And I photographed the region in front of my home, hoping that I could pull out the comet, but all I got was this picture. But here's the area of Scorpius, the Scorpion. And my vantage point, my viewpoint, I have mountains on my western slopes. And so that compromises the view of Scorpius. So your results may differ, especially if you get out to a dark location that has a low horizon. You still have some time to observe some great objects in the constellation Scorpius, the Scorpion. And here's the Scorpion drawn. And near the Scorpion is, of course, Sagittarius, the Archer, or the teapot shape. And that's still fairly high in the sky. And then here's a number of great objects for binoculars or for beginners to hunt for in this area. And so September is usually last good opportunity to get this part of the Milky Way before it starts dipping lower and lower and disappears for the winter. But this is the area that I tried to find the comet. And so I took a photograph with a different lens with a narrower field of view in that area, and it doesn't show up at all from the city. But I suspect if you had a telescope and a camera on the telescope and you dialed in the coordinates, you would be able to pull out that comet, but it should be right there about now. And it's going to be dropping lower and lower. So start by next weekend if you want to try to get a capture of that. I'm going to try to get it next weekend. Anyway, this picture was taken at another time at another place, but it also shows the area of Scorpius and some of the other objects in the sky around Scorpius that you may enjoy hunting for. And then if we continue up the Milky Way galaxy, that big, huge lit area you see in the picture goes up overhead in the early evening. So it's a good time to view other objects in the Milky Way. So if we follow that path, we get a better view of Sagittarius. And the region between Sagittarius and Ophiuchus, again, has a very bright section of Milky Way and also some dark nebula in it. The one here kind of famously, the Pipe Nebula, but it looks like a horse. So it's fun to pretend that's a horse when it shows up in your pictures. And then there's a lot of objects over here just above Sagittarius, some globular clusters, some open clusters, some nebula. And so this particular area has a lot of beautiful stuff for binoculars and small telescopes and large telescopes. And then if we continue up the Milky Way, and I've continued up, but I've now rotated my picture so that it can use the full screen. And this is the region where we come to Aquila the eagle. And I'm never sure how Aquila is supposed to be portrayed as a figure, but the way I've drawn here is one way that I often see it. And around Aquila, there's a number of deep sky objects, a number of globular clusters, and a number of open clusters and dark nebula, such as this one in Bernard's E, which shows up pretty well if you had a dark location and using a camera to get the area. So M11 is often a big favorite cluster to see in small telescopes and even large telescopes. And then binoculars, this over here often called the coat hanger. But I always think it looks like a kid who has tied a little bandana for a knapsack on the end of a stick, and he's running away with a bag of peanut butter sandwiches until his mom notices him. So that's how I've always seen this particular cluster of stars myself, but that's Brocchi's cluster, or the coat hanger. My favorite object right now, I'm obsessed with planetary nebula. The reason is that you get your camera on them. You don't need the best photographic skills, but if you can get a camera maybe coupled at prime focus on a small telescope for the region, pointed at that region where there's a planetary nebula for just like even 30 to 60 seconds, often they'll pop out on your camera image as this green little dots. And so I find that very exciting to just discover and find many of those. So these are some planetary nebula, which are stars of size mass around the sun that weren't big enough to explode into a supernova when they died, but instead just coughed out their outer layers. And now they're illuminating their outer layers. And so this area has a lot of objects, from planetary nebula to globular clusters to open clusters to dark nebula. That's the area around Aquila the Eagle. And if we go a little farther, we come to the constellation Cygnus the Swan. And here's some of the animal portrayals of that. For a lot of the star parties that I've been doing lately, we do them for schools, and I've been doing a lot more with animal constellations where I let the kids guess the animals as drawn, and it seems to be going over pretty well. So I'm redrawing all the animal constellations in the sky. And anyway, in this region, there's a number of, I believe all of these are planetary nebula, and some of them are easy to see in a telescope, such as M57 up here, the famous Ring Nebula, and then M27 over here is even showing up on this particular wide field photograph image that I made. And so you can actually see the little green dot there. That's probably one of the two brightest. I think it's like the second brightest planetary nebula. I just read recently that another one was brighter, or the second brightest. I have to look into that myself later. But anyway, these planetary nebula are nice to see. This one over here, NGC 6826, is known as the blinking nebula. In most medium-sized telescopes, it's just bright enough that if you look away for a moment, it disappears. And so it blinks on and off. But otherwise, a lot of these so far are hard to see in a telescope, but they do show up rather nice on a camera. And here's other objects in the area. And again, with Cygnus the Swan, it's high overhead early in the evening, so you can get a couple hours looking at the region, bringing in various objects, including the Veil Nebula if you have a larger scope, and or photographing it, and then the North American Nebula here also. And here's some of the nebula pictures that I've taken with my prime focus setup on my telescope, and they're not to scale relative to each other, but here's like the M27, the Dumbbell Nebula, one of the brighter ones, visible with binoculars at a dark site and very easy to see in a telescope. Same with M57, very easy to see in a telescope, though small, needs magnification. Over here is the Blinking Nebula. And these two here, NGC 7008, is just beyond all I have to do to get that one better is take more images and learn how to stack them properly. So things like that are kind of an exciting opportunity because it has area to it. It has a certain amount, you can actually see some area. So you know there's something that I can do if only I improve how I handle my photographs. I don't need new equipment to do that. I can do that just by learning how to use my equipment better. Same with this one up here, NGC 6781. It's got some size to it, so a little more work. I should be able to get that shining better. Anyway, so these are some favorite planetary nebula of the region. And considering how hot it is, I thought I'd end with just a little hope for the onset of winter, the promise that winter is coming. This time of year, if you stayed out all night and got up in the early morning hours, this would be your view to the east. And I took this picture last year when I was helping out at the Joshua Tree Dark Sky Festival, which is going on the weekend of the 24th this month again. And so I camped out. In all the years camping out in the desert, I've never encountered bugs, so I now just go out there with a cot and I sleep in the open. But what I discovered last year might also apply to this year. Apparently, it must have rained just a few days before, because I woke that morning to just the a chorus of mosquitoes buzzing all around my head. And so I really just couldn't stay there and just fight them. I just got up and took some pictures. But now with all the rains we're getting, if you're going out to the desert, be prepared. You might see, you might be swarmed with mosquitoes just as I did. So anyway, this is a winter constellation. You can look at it and think, oh, winter is going to come. We're going to have cool days again. That's the bright star Sirius in the morning, the brightest star in the sky. You can see M41, an open cluster next to it. And if you go a little higher, of course, anytime you photograph higher, you get a clearer image because you're looking through fewer mosquitoes. And so here's of the Orion constellation, Orion, fairly high in the morning. Again, another reminder that hang in there, winter is definitely coming. Thank you.
That was great, John. Thank you very much for yet another great What's Up. We really enjoy seeing all your illustrations and photographs each month that you do the What's Up presentation. And as mentioned in a comment by one of our audience members, we miss seeing your assistant. How's Emma doing?
Yeah, Emma has a job at Amazon in Corona, and so she just works and sleeps and talks about how tough it is to be working in this world. Actually, I made that up, but I can see her going through that growing pain of understanding, appreciating what it's like to hold on a job. But she's not giving up on astronomy. She'll be back someday. Thank you for
wonderful.
Asking.
Sure, we will love to see her again.
Yes.
And thank you again, John, for a great presentation.
Thank you.
So my name is Reza, and I'm the Vice President of the club. I, too, would like to welcome you to the September 9th, 2022 General Meeting of the Orange County Astronomers. Our speaker at this meeting is an astroparticle physicist and space scientist. He's an associate professor at the Department of Physics and Geology at the University of Perugia, Italy, joining us in the early mornings. His research interests include cosmic rays, dark matter, antimatter, heliospheric, and space physics phenomena. He's part of the Alpha Magnetic Spectrometer collaboration for the search for dark matter and antimatter in space. Please join me in welcoming Dr. Nicola Tomasetti. Nicola.
Thank you, Reza, for introducing me. Thank you also for the invitation. Very happy to be here. And yes, it's early in the morning here. I'm sharing my screen. I hope you are.
Yes, we are seeing the
my slides.
Yes.
Trying to set full screen.
Perfect. All good.
Okay. So talking about cosmic rays and their connection with antimatter and dark matter. I think it's going to be a confusing talk because it's also a confusing topic. Hope you will be able to follow my stream of consciousness. We start from cosmic rays. All of this is about the observation of cosmic rays, their main properties, and what this led to us. We know now that cosmic rays are continuously passing through our bodies, and every second we are crossed by hundreds of these particles. Of course, they are invisible, we don't see and we don't perceive them, but it's a constant rain. They rain down to Earth. Here is what we know now, that these particles are of extraterrestrial origin, and they reach the Earth from the outer space, coming from every direction. So they are, in some sense, messenger of the cosmos, like other. We have several questions that can be addressed when studying this kind of radiation. What they are made of, what's their nature, where do they come from, and what we can learn from cosmic rays and how can we measure them. When I say they are messengers, I show you this sketch. We receive several kind of particles from outside the Earth, from the universe. Not only light, but also neutrinos, cosmic rays, gravitational waves, and maybe something other. WIMP is a name for indicate dark matter particles. I'll come to this later. Anyway, we have many means, many tools to look at the universe if all these particles are considered as messengers. Cosmic rays is in some sense a unique messenger because it's matter. It's not I mean light like what we did for several centuries. We used to look at the universe from the light emitted from the sources and studying, and this allowed us to see the universe and to study the sources. Cosmic rays, in some sense, are a real sample of galactic or extragalactic matters that comes to us. Now, with this scheme, it's what we do when we do astronomy. We just collect light coming from some direction, and this is a very ancient activity. Here is, for instance, historical attestation of cosmography in the Bronze Age, in the Nebra disk. It's attempt to represent the sky, the sun, the moon, and the Pleiades. Here is another big step in the astronomy when Galileo used to start to using the telescope for scientific observations, and this is maybe the birth of modern astronomy. And from the study of the only visible light after millennia of observation, in the last century we opened this study to the whole electromagnetic spectrum. Here is what we call the multi-wavelength astronomy, receiving radiation from sources at all the wavelengths, and also looking at the whole sky. This is a recent example on how can be observed a tiny portion of the sky with very high angular resolution in the infrared. Here is the full sky, where we see the structure of the galactic plane with visible light. The same photo can be done in using gamma rays, for instance, and we see a different universe because there are different phenomena emitting gamma rays, and this can be studied at many wavelengths. But if we look at the universe around at the sky using cosmic rays, what we see is something more similar to this map, something almost without information. That's why, because cosmic rays reach us from all directions, so the arrival direction are essentially random, and the sky map we obtain is isotropic to a very high degree. And this seems disappointing at first because it's saying, but what kind of astronomy can we do with looking at these particles if we have essentially no information from the direction? And you see, if we come back to this scheme, what I I draw the trajectory of this particle pretty twisted, because this is essentially the reason why we don't see the sky using arrival direction of cosmic rays. We don't see images. And the reason is related to the nature of these particles. And in fact, in some sense, this simple observation, very basic observation about the high level of isotropy of cosmic rays tells something about the nature of this particle. We know cosmic rays are charged particles, so they are sensitive to magnetic field. In the galaxy, everywhere in astrophysics, there are magnetic fields that deflect and randomize their trajectories, so their motion is becomes highly erratic, random. And here is why we don't have a spatial information, and we can't identify directly the source where they come from just by looking at their arrival direction. This is part of the game. It's the observation of anisotropy is what it tells in the first place. They must be charged particles. When they were discovered more than 1 century ago, they were actually called ultra gamma radiation at first. It was believed they were gamma rays, so high energy photons. Even the name cosmic rays actually does not suggest they are particles. It comes from Millikan, who believed they were high energy photons emitted from the birth of the universe, from the Big Bang. This theory had several other many changes, but we know after since the 30s, thanks to Bruno Rossi, that these particles are charged, electrically charged particles, and they are atomic nuclei. So the questions remain: where do they come from? What's their nature, and how to measure them? Here is just a scheme of these errors that are particles coming from outside to our Earth. But we should also, to be more precise, put the atmosphere and note that these particles would interact with the atmosphere because they are charged particles and the atmosphere is made of atoms. And what happens is that this interaction produces secondary particles, a cascade, with the structure like the one sketched here. Maybe here it's more precise. Because cosmic rays are nuclei, essentially, protons, atomic nuclei, that encounter other nuclei from the atmosphere, like oxygen or nitrogen, typically. And in a high energy nucleus-nucleus collision, what happens, and what we know very well, thanks to several experiments at accelerator, is that these particles produce hadrons, other particles, and so on with a cascade. And what is raining down at the ground, what we are reached from, is actually only muons and neutrinos. So what we what we call cosmic rays, what Victor S. used to call cosmic rays, Bruno Rossi, Milik, all these people 1 century ago were actually muons, not what was really coming down from the space to Earth, but a secondary part. And if I go again to this representation, so we are reached by all these particles, but as long as we are at the ground, protected by our atmosphere, we observe only a shower of secondary particles. And here is our shower is developed. They are giant structure and can be, of course, studied, experimented by several ground observatories. What we see is that the primary particles actually maintains the direction in the shower, but it disappeared the first interaction. So here is the motion of the axis, the center of mass of the system, and the system is composed by million, not billion particles. In this shower, actually, we have high energy collisions like what we can reproduce now in accelerators. But in the last century, it's how many elemental particles were discovered. Like in this timeline, we see the discovery of the positron in the 30s, the muon, the pion, the kaon, and other elementary particles were done in cosmic rays, in the shower. All these particles were discovered because they were produced in these collisions in the atmosphere, and we were able to detect them. Then, with the advent of particle accelerators, like the one we have at CERN or at Fermilab in Chicago or SLAC, and it was it was the era of experimental particle physics, where several new particles were discovered, like the antiprotons, the antineutrons, neutrino, and many mesons with hadron spectroscopy. And from this epoch on, cosmic rays are now regarded today as a messenger, not as a tool to where we found new particles. It's important that also the positron was discovered in cosmic radiation, because positron is the proof of antimatter. Positron is the negative, the positive electron, the antimatter partner of the electron, and was first predicted by Dirac as a solution of the Dirac equation. The Dirac equation was his attempt of describing the electron, putting together quantum mechanics and spatial relativity. So it's a generalization, it's a relativistic generalization of Schrödinger equation. But this equation had two solutions that couldn't be neglected. One was the electron solution, and the other was then interpreted by Dirac itself as an antimatter solution, or something that behaves like the electron, like matter, but with opposite charge or opposite energy, was noted by Dirac. But now we have a well-established theory for antimatter, and we can produce easily in our laboratories. It's also used in medical application, in particular for electron and positron. So it's very, very, it's normal matter. It's ordinary matter. It's just the puzzle is why all these antiparticles are absent in nature. In the sense, we know they exist. We know they can be produced in high energy collision. We know how to produce them, but we don't know why. If we look around at our world, but also at the universe, we have no traces, no big traces of antimatter. And so there, it seems there is a secret. Here is an example, like if for every particle we have an antiparticle. Then we could think of anti-atoms, anti-nuclei, and even other structures in the universe, like anti-stars. Why they don't exist? We don't see anti-stars. But if we go to the Big Bang, the beginning of everything, we should start with a symmetric situation. If any, because if from nothing we have the universe and charge is conserved, is the conservation of charge is one of the really most fundamental things that that resist to every test. It's quite pretty natural to think a symmetric situation in the beginning where matter and antimatter are equal in terms of abundance composition. So what happened? Why now we see that our universe is asymmetric? It's an open question. One possibility is that matter became dominating over antimatter in the course of the evolution of the universe in the initial stage, in the thermal evolution of the universe after the Big Bang, and that's probably the most accepted idea. But another idea is that, well, globally, the universe is still containing matter and antimatter in equal abundance, but we live in a large domain made of matter. But if we were able to look at a very large distance, we could detect or see very large domain of antimatter. So possible that the universe on very large scale is still symmetric. It's hard now to discriminate on these two hypotheses. And of course, the first hypothesis requires some mechanism to explain why this asymmetry. In the second case, it's true that as we should have a kind of anti-universe. Like if we have, we live in a galaxy with stars, we look at planets. For what we know of fundamental interactions, also antimatter should be able to form structures, complex structures, and cosmological structures, or even anti-galaxies. Just we don't see right now them, but it's we can't exclude large regions of the universe with anti-galaxies. What would be the signal to look at them? One possibility is that if there are such regions, there might be boundaries between antimatter regions and our matter-dominated universe, where the particles encounter, they annihilate, and we may receive gamma rays. We may observe gamma rays from this boundary. But the search was done from several gamma ray experiments, and for the moment there is no sign of this. Another idea is if there are anti-stars, we would expect a similar nucleosynthesis process, and there must be anti-carbon nuclei around. So the detection of even one very convincing proof of an anti-carbon nucleus from the space would be a very strong proof that this come from an anti-star, because it's hard to produce an anti-carbon in other and to explain its existence if we find this in space. Now, this was a big parenthesis on the antimatter. Let's go back to cosmic rays and our problem detection. If they are destroyed in the upper layers of the atmosphere, and we receive early secondary particles, to study these particles is a bit of challenge. How we do? We could follow a indirect detection method. It means that from the ground we observe the very final secondary particles of the shower, and then infer the properties of the primary particle to generate the shower, and it's quite challenging. Or we go to space to reach cosmic rays before they are destroyed by the Earth. And in fact, it's since the space era in the 50s, and after that, much progress was done in cosmic rays because the real what we call primary cosmic rays are not the particles that are crossing our bodies, but are the particles reaching the Earth from outside. And to have a direct detection, we need at least a stratospheric balloon to reach very high altitudes, or even better, the satellites, the space station, or the space shuttle, or even probes like Voyager, Ulysses, or Pioneer. So there are many experiments right now and in the last decades observing cosmic rays from space. Here is the sketch. This is since the 2000 to date, so last 20 something years of all experiments measuring cosmic rays in time. The red points are balloons, experiments on balloons. Every balloon flight is usually very short, to be 1 or few days, at the most 1 month. While the experiments in the space, like Pamela on satellite or the Fermi Gamma Ray Telescope, those experiments are can be of very long duration, years. Like here, the alpha magnetic spectrometer and the CALEP experiments. They are both on the International Space Station, and this on the bottom is the Voyager probes, but also there are also other small spacecraft that made in the years several measurements of the cosmic radiation from space. So the cosmic rays are very well studied from space, and this is in the present epoch is really a golden age for the measurement of cosmic rays. There are really several experiments currently active in providing data. What is when we talk about measurements? What we measure is usually the flux. What we call a flux is the intensity of this radiation. Imagine we have a detector, like a box, a cube, crossed by this particle. We count how many particles traverse our instrument, how many particles per unit of time, so per second, but also per energy and per surface and angular solid angle. So once we are able to count particles, we can also make studies like analyze the composition of these particles, if we can identify the mass or the charge, or the isotope, depends on the species in general. So we can study their energy distribution, their arrival direction and angular distribution, and if this flux is subjected to temporal variation or constant, for instance. And this is all the information we can get from cosmic rays. So we don't get image usually like what is done with gamma rays, but several, for instance, spectral information, composition information, and they are interesting in many ways. This graph, this plot shows how the flux, so how the intensity of the cosmic radiation changes as function of energy, and it's a log plot. So it spans what we see is that the cosmic rays have a very wide energy range from fraction of JeV to very extreme energy that we would never reach with our accelerator. And for just having some idea, the LHC, the most powerful accelerator, we have it here, 10 to the 13, more or less. And this is a logarithmic scale. So it's really the radiation of cosmic rays can be really energetic compared to what can do by, on Earth. But the spectrum is decreases as a function called power law at increasing energy. So stronger is their energy and less intense is the flux with a rapid decrease. And this shape is very peculiar for the spectrum. It's not so common in astrophysics having power law. It's common but it's very common in general in nature, encountering this kind of distribution. In astrophysics, especially traditional astrophysics like stellar or galactic astrophysics, distributions are, we call them thermal because they originated from collisions of particle energy exchange and they are related to the temperature of the system. This is a typical non-thermal distribution. And it originates from some non-thermal process that we know it's the common astrophysical process to generate this kind of distribution is the shock. This is also called the power law, the zip law, and it's also can be found in other contexts, but it's pretty common actually in like in social science or well in many fields. For example, here it captures the relation between in general between the frequency and their size, but it can be this example is in the distribution of the wealth, or the GDP of the countries. Like here is the wealth of the most rich people as function of their ranking. So it's an old plot where we have Bill Gates, for example. And if we do this distribution, we found a power law, not different to the cosmic ray spectrum. Now, there is no direct relation, of course, but there is, if one starts thinking about this power law, can maybe get some idea of how these particles are accelerated to this energy. What's the origin of this particle? And this is what Enrico Fermi, did in 48, 49, when he came out with a theory of this radiation, a theory for the origin of cosmic rays, because the question was what physical, astrophysical process can produce a power law and can produce particles of such extreme energy. And Fermi proposed in this paper a mechanism for the origin of the cosmic radiation related to the interaction with moving magnetic fields. Now we know what we know. We have now a more precise idea of how cosmic rays are accelerated, and the mechanism, the standard mechanism of cosmic acceleration is still based on Fermi's idea. Here is a sketch is illustrating the idea. Actually, we know that we believe that the sources of these particles are supernova remnants. So when a star explodes, these explosions generate shock waves that can accelerate cosmic rays. And they can justify the intensity of the spectrum from the energetic point of view. So the supernova remnants are the best candidate as sources of cosmic rays for just for the energy budget point of view. But regarding the mechanism, what Fermi proposed is that cosmic rays are accelerated by moving magnetic clouds that can be, we can think of it like two mirrors or two trains here moving each against the other, and we see if we have some particle bouncing with the moving a moving wall or mirror. At every bounce, it gains some energy, and that's the idea. And this idea is actually can be realized in nature in astrophysical shock, because when we have a shock wave expanding in space, we have a plasma dynamics such that every time a particle crosses the shock, this particle is randomized by magnetic field, and when it gets the other side of the shock, it's like it's like bouncing on a moving magnetic mirror. And these shocks are studied very well because the structure of the expansion of a shock wave is really similar to an atomic explosion on Earth, for instance. But of course, in the astrophysical environment, we have different environment, but it's by the point of view of the basic mechanism, it's not so different. So shocks have been very well studied in Los Alamos, for instance, in nuclear tests. And what we know in this mechanism that every time a particle crosses the shock, it gets energized. To reach the very the highest energy, many crossings are needed, of course. So only few particles are able to stay around the shock, crossing it many times. It's just a random process. It's like throwing a coin, tossing a coin, and having the same result for a long sequence of tries. It's not a probable process, but a few particles can reach the highest energy, but while the bulk of particles, many particles will cross the shock only a few times before they get lost in the intergalactic space and reach us. So this explains why this distribution, power law distribution, which decreases rapidly with energy, so that the bulk of many particles are distributed at low energy, and only a few particles at high energy, but they can reach very high energy. Like it's also the power law related to the Pareto law, and here is the connection. And supernova explosions are everywhere in the galaxy. They happen with a frequency like 3%. So not a strong frequency for us observing this phenomena, but by the point of view of cosmic rays that stay millions here in the galaxy, we have several supernova explosion activity in the galactic plane, like illustrated here, that continuously inject cosmic rays in the galaxy. And once in the galaxy, cosmic rays can travel. And since the galaxy is a magnetic structure, has not only stars and radiation, but also strong magnetic fields, it can be, by the point of view of a cosmic particles, a charged particle, the galaxy is a giant magnetic trap. So cosmic rays are confined in the galaxy, and they travel randomly because the fields are turbulent for millions or tens of millions years before eventually escaping or interacting or get detected by us. So here is again the idea of why we receive a high level of isotropy when looking at the rival direction of cosmic rays, but just looking at their spectrum and their energies, we have an idea of what their source could be and what can happen in the galaxy. Also, this irregular pattern, this erratic motion in the galaxy can be treated as a diffusion process. Diffusion is also a fundamental process very known in physics. It's a Brownian motion of a particle that has scattering in a medium with other particles, so that its motion is completely random at some point. This is what happened to cosmic rays, but it's also what happened to many physical systems. So it's very well studied, and it's the process, we believe, how the propagation of cosmic particles in the galaxy is realized. So the standard, what we call the standard model or the standard paradigm of cosmic rays, is based on these three pillars: the acceleration process in the shock waves, probably of supernova remnants from supernova explosions, and their transport in the magnetic field, which is a random walk process or a diffusion process related to the magnetic turbulence. There is also a third pillar that we now discuss, that it's related to their interaction with the other particles of the galaxy. And it's very important because this can be related to the generation of antimatter. Here is just another sketch. It's like a cosmic ray physicist sees the galaxy. It's not so important that it's a spiral structure for the Milky Way, but it's important to look it as a box, a cylindrical shaped box where cosmic rays are confined to stay. And they travel with random motion, and they stay there for millions of years. So it's like a box full of filled with a gas of charged particles. If we look at the composition, particle by particle, we count and we ask what this radiation is made of. We know well that it's made of atomic nuclei. So no exotic species. These are the elements we know, and essentially all elements of the periodical table are in the cosmic radiation. But it's really interesting also to look at the abundance and compare them with the abundance of the world of known elements. We look the main components of the cosmic radiation, and we see that it's not very surprising, having most of them are hydrogen nuclei, so are protons. 10% or less are made of helium nuclei, and then heavier nuclei like carbon, oxygen, this common iron, nitrogen, silicon. So this is more or less the composition also of elements in the galaxy, in the stars. Not apart from the precise number, nothing much special. Also electrons, of course, are there. We can also measure the antimatter components. We know that there are several positons. One positron over 1,000 protons, or one positron over 50 electrons, and one antiproton over 10,000 protons. And the antinuclei have not been observed so far, only calculated. But the search is ongoing. But this one antiproton over 10,000 protons, it seems a little number, but it's actually a very huge number. This is an example. This is old popular Italian car, Fiat Panda, this car is made of the weight is a ton more or less, and this red element is the rear mirror. This mirror is like 100 grams of weight. So if in the what I mean here, this proportion, one antiproton over 10,000 protons, means that it's more or less equivalent to having this mirror made of antiprotons and the rest of the car made of protons. It's a lot of antimatter. We don't have so much antimatter in the world. We have essentially, if we look at the most common things, the proportion antimatter to matter is zero. We can say it's zero, not the 1 over 10,000. This means 0.1 per mil. So it's a lot. So this observation said that there is a very large fraction of antimatter in cosmic rays that has to be explained. We have two theories that we will discuss. One of is collision of cosmic rays, the interactions with the gas that can produce antimatter, and the other can be related to dark matter. Of course, it's more speculative. But if we look again at the composition of cosmic rays, we said there is hydrogen, helium, most common elements. But another peculiar aspect is that if we compare cosmic rays composition with the composition of elements in the galaxy, not in cosmic rays, but in the interstellar medium, or even in the solar system, what we have is some strong discrepancy for this nuclei, for instance, lithium, beryllium, and boron. Like boron or lithium or beryllium are very rare in astrophysics. Everywhere are rare. We are not made of lithium, for instance. We are made of carbon. But in cosmic rays, there are a strong overabundance of these particles. We can look here, if we look at the abundance of elements in the solar system, red, and in cosmic rays. There is a strong excess of lithium, beryllium, and boron here. And there are also other excesses, like here of titanium, vanadium, chromium. There are some elements where there are some discrepancies. And this gives us some indication of interaction. In fact, the idea is that these elements that are absent in stellar nucleosynthesis, so they are absent in stars, so they are absent in the most of astrophysical environments. They are produced in cosmic rays, and that's why we observe them in interaction. An example here: the collision of carbon nuclei in cosmic rays with the gas. Gas is just interstellar, the gas of the galaxy, the particles that makes the galaxy, the galactic plane, the interstellar gas. And these collisions can break the carbon nucleus in smaller pieces. Here is what happened in this sketch. Carbon nucleus might hit the gas. With the collision, it breaks in lighter fragments, but still energetic, because the carbon is initially high energy nucleus, the fragments will maintain this energy. So a carbon can break and produce lithium or beryllium and or boron and other fragments. The boron, we can have a cascade where also the boron can break in lighter elements, but the point is, from carbon or oxygen or iron, whatever nucleus, we can produce particles that otherwise we would not observe. And this is what happens continuously in the cosmic radiation, because they are high energy particles. And this process would explain the abundance of lithium, beryllium, and boron. Of course, it's not single process. It's a chain of nuclear reaction. So it's difficult to track the whole chain and to explain the abundance. This is, for example, it's a complex plot here, but it's my attempt some time ago to track this chain of reaction to account for explain the abundance of boron and beryllium in the cosmic radiation, and it can be explained just from the initial fragmentation of carbon, oxygen, silicon, and other elements like also iron, magnesium, the most abundant in the universe and in cosmic rays, and can explain more or less this. Now, with antimatter, we expect that the same should happen, like proton collisions, that proton is the most common element in cosmic rays against the most common element in the gas could produce antiprotons, for instance, or positrons in some hadronic interaction, not different to the showers I was speaking before in the atmosphere. But this could happen also in the galaxy, with the matter of the galaxy producing these particles. So if the point is here, if antinuclei are, if the rare antiparticles, like if the rare nuclei like lithium, beryllium, and boron are produced in this collision, and we observe they are abundant in cosmic rays, we then must observe also some overabundance of antimatter. And this can explain why there is so much antimatter in the cosmic radiation, because of the same kind of collisions that explains the nuclear abundance. But there is also another possibility. The green collisions is, of course, the standard explanation, and this is a existing mechanism. It should take place. But there is also another very interesting phenomenon that it's related to the dark matter. And dark matter, the annihilation of dark matter particles, if they exist in their galaxy, can produce antimatter. We can look better on what is dark matter. It's, of course, one of the most important open questions in astronomy, cosmology, and astrophysics. If we do the energy budget of the universe, we know that 70% of this energy is dark energy, and we have no idea of the nature of what's dark energy. It's just something missing in the energy budget. But also interesting is the remaining 30% of matter, because only 5% of this can be explained with known matter, with the elements, atoms, nuclei, etc. While the remaining 25% is something that we call dark matter. More precisely, we call non-baryonic dark matter, which means that is not only dark in the sense that it doesn't emit radiation, but it's already made of unknown particles. They cannot be particles from the standard model of fundamental interaction. There should be new. This unknown substance should be made of some new particles with very peculiar properties. But we don't know. What we are sure is this kind of matter should interact gravitationally to form structures, astrophysical structures, to interact with the matter in this way. But we have no evidence for other kind of interactions with the matter. So it's highly difficult to detect this part. of course, dark matter is known from its only gravitational interaction, and the only evidence we have for dark matter is related to gravitational studies, so to the study of dynamics of large objects. In the 33, it was discovered by observation of Wiki of the Coma cluster, where from the dynamics of the visible matter of the galaxy, he estimates the presence of a giant halo, dark halo of mass that was like 500 times more than the visible mass. There was a halo of dark matter in this cluster, and then we discovered that dark matter is essentially everywhere in all astrophysical systems, and in particular in galaxies. This was studied better thanks to the advent of radio astronomy, and in particular with the studies of Vera Rubin, who studied the rotational curves of spiral galaxy. What she found is that the velocity of the most peripheral stars was too high compared to the velocity they were supposed to have if the matter of presence in the galaxy was only the visible matter. So what was measured here, thanks to, in particular with the radio astronomy observation, is the velocity of the stars as a function of the distance from the center of the galaxy. In several galaxies of a spiral form. Spiral, because when the spiral galaxies are those where stars are located in forming a plane, well easy to identify, so the velocity field of the stars can be measured more easily. Here is an example of a simulation of a galaxy with dark matter, without dark matter in the left and with dark matter in the right. It's by eye, maybe it's not hard to see the difference, but the difference is if we go to move away from the center, the velocity of the stars generally decreases. So they are faster when closest to the sun, because a galaxy is not a rigid body. It's a so the rotation is differential. They are more or less dragged related to the gravity, of course, but in a peculiar way that can be also related to the Keplerian studies. The same happening also in other scales, like in the solar system. But if we look at the right plot, if in addition to what we see, the visible stars that are points, we add a halo of matter, of dark matter, invisible but gravitationally interacting with the whole system, the rotation is more similar, not a rigid body yet, but more similar to a rigid body, more, I would say, faster in the outer regions. And this is closer to the observation. Now, it is one of the key observations that established the presence of dark matter. Today, dark matter is a basic component of the formation of the structure, so it must be there in all astrophysical systems. And it's every galaxy is surrounded by a halo. This is a representation of our galaxy, and a dark matter halo, the blue, which is actually much bigger than the galaxy itself. And this halo, this dark matter halo, we don't know, but it must be made of particles. And here, these particles is what we call WIMP. WIMP means weakly interactive massive particles. It's just an acronym to state what these particles should be have. The interaction should be weak, because we don't see actually their interactions with the particles. They should be massive, of course. The idea is that these WIMPs played an important role in cosmological formation of the whole universe, in particular after the Big Bang. Okay, it's a long story. But the important thing also is that we should at some point interact with matter. It's just that their interactions are very rare because of they are weak, like neutrinos, so are weak and are dark. But at some point we are able to detect them, and if they interact, they might collide and annihilate and produce standard model particles, SM, standard particles like known particles, and we may able to detect this particles. So if the galaxy, our galaxy, is surrounded by a dark halo, as it seems, and if this halo is made of particles, at least occasionally, we should have this process where dark matter particles interact with themselves with other dark matter particles and produce uh, standard model particles that we know and we can detect. And in this final state of standard model particles, we may have antimatter, which is otherwise rare. And this process can explain why there is so much antimatter in the cosmic rays, because this antimatter produced in this mechanism should also be energetic, because the initial particles are massive, and this mass is converted in energy in this process. Of course, it's a process. It's a speculation. Looks like a speculation, but it's the theory behind it is pretty solid actually. And in some sense, the final state of this process are the messenger for dark matter, and the current search for dark matter annihilation signals are focused on the photons, gamma rays, neutrinos, or antimatter particles. And this annihilation can take place everywhere in the galaxy, but of course, where dark matter is more concentrated, so we believe in the galactic center. So what we expect from antimatter? What we should observe? We can expect a spectrum of a flux, say, as function of energy of these particles from the dark matter annihilation, with a bump-like function like this, where the intensity has a peak and then it decreases. And this, if we detect this shape, we can have information of the dark matter annihilation rate on the mass of these particles and on their interaction. The annihilation rate is the strength of their interaction, because it gives the probability they interact and they produce matter. So from this signal, this is the dark matter signature we may search by looking at antimatter particles in the cosmic rays. And we have also what we call background, which is the process we already have seen when cosmic rays interact with the gas and produce antimatter particles. In this process, standard process of cosmic ray physics, we expect a power law spectrum, energy spectrum, not different to the power law of other cosmic rays. So we may have a signal, an excess over the background that could be in principle observable, and could be our proof that, looking at that matter, our proof that dark matter is made of particles, and could be a measurement of dark matter properties, the nature, the particle nature of dark matter, like the mass, its cross section, new physics, of course. Of course, it's hard because we have to know very well the background and measure the signal. That could be very challenging. Now, this is actually the main goal of various experiments, like the alpha magnetic spectrometer experiment, which is the most ambitious experiment for searching of dark matter signals in space. This is a big device. Actually, it's a particle physics experiment in space, and it operates on the International Space Station. This is just the logo, the experiment that shows, you see, it represents also the Big Bang, the universe, and the hypothetical anti-universe, because one of the goals is to search also for antinuclei like anti-helium or anti-carbon that would reveal the existence of anti-astronomical objects. The AMS is an international collaboration led by Samuel Ting, who's from MIT, but usually based at CERN in Geneva, where is the headquarters of the experiment, where we have the control room, and the experiment is in space. It's this instrument, this instrument of the left. It's like we can imagine like it fits in a cube of 3 meters of side. It seems I mean it's not a so big object to be a particle physics experiment, because the experiments in at CERN are much wider than this. But it's an incredible huge object if we consider that it's running in the space station. So it was launched in the shuttle. Here is a photo of AMS installed inside the space shuttle way in 2011. Here is the launch, and here is a picture of AMS installed in the International Space Station, and it's still there and still working. So it has more than 10 years of data taking. It collected more than 200 billion particles far. And sorry, let me see. Okay. And it's a detector for antimatter. Means that inside this instrument there is a big magnet, because charged particles are sensitive to magnetic field, and they are deflected by magnetic field. And this is the way matter and antimatter are separated, discriminated. So the detection of, for example, a nucleus of anti-helium from a nucleus of helium, they behave the same in all aspects, but using a magnet we can track the trajectories of the two, and we can say if this particle is an helium or a nucleus or an anti-helium just looking at the sign of its curvature inside the magnetic field, because they have opposite curvatures. And it's the way AMS experiment uses to detect and to search for anti-helium, but also antiprotons, positrons, etc., to search for antimatter. Here is a result from the flux of cosmic ray positrons as function of energy. You see, in green is what we expected before doing the measurement from the collision of cosmic rays. So the measurement actually revealed there is a very strong excess. And at the very first, when this measurement was released, actually it was the first thing you think is, oh, there is a big dark matter induced excess. So dark matter exists here. It gives a peak at about 3, 4, 500 of JeV. So it says this says a lot about the nature of dark matter if the interpretation is correct. But it's actually hard to interpret this in terms of dark matter because it's too strong and too massive for the theory, for what we believe are the dark matter properties. So the question is still open on the origin of this large excess, but very good explanation could be that in pulsar there is a known mechanism that can produce high energy positons, explaining this excess and this feature from the emission of positons in the magnetosphere of pulsars. It's a very sophisticated mechanism, but could work and could be an alternative to dark matter explanation. But this measurement is very passive. Here is some newspaper in 2013 when these data were released preliminarily, where, for example, Le Monde, Matière Noire or Pulsars, Dark Matter or Pulsars. This is the most honest title, I think. Other were mostly about dark matter, but anyway, there was a big hype in the scientific community. We then came with the measurement of antiprotons, and at first glance, what we see is, seems that antiproton data are quite well consistent with the background. What we call background is the calculated flux of antiprotons produced by collisions. So it seems that for antiprotons, there's no big excess. Actually, if we look carefully in this region, it seems there is some little discrepancy, some more antiprotons in data than expectation. And in fact, this is a log-log plot. This could be explained in terms of dark matter, and many authors claimed that there is a small excess, but it's a tiny excess. But actually, from one side, the properties of this small excess and the properties we can infer from dark matter particles given this excess are very promising, because are the desirable properties that in cosmological models are needed for dark particles. So it seems very making sense. But it's so small, the excess, and the discrepancy in fact is so small that it's hard to claim safely there. We need to understand more the background, the uncertainties in these estimates to have a better evaluations. And another idea is to look not at antiprotons but other particles. In particular, in the search ongoing is for antinuclei. So not antiprotons, but nuclei composed by antinucleons, like antideutrons made of antiproton and antineutron, or antihelium, that is a nucleus made by two antiprotons and an antineutron. These antinucleus can be produced from collisions, of course, and we know this from experiments at CERN, LHC. But the interesting thing is that for this nuclei, the background and the dark matter signal are can be very different. If I go back here, you see signal and background are confused, and the signal is much less intense than the background. So it's 1 order 10 times more, 10 times weaker, the signal. So it's hard to claim to find an excess. But for antinuclei, from calculations, we know that the signal, the dark matter signal, the blue line here for antideutrons, is in excess of any reasonable calculation of the background here. And this means that if we were able to detect antideutrons or antihelium, we would know if there is a dark matter excess of this type, of the type discussed before. And this would provide a conclusive answer. Unfortunately, so far, since these fluxes are very weak, because both signal and background are very rare processes, so there are really few anti-nuclei in the galaxy, but they must be there, at least for the background. So it's hard to detect them. But AMS would have some chance, and other experiments in the future still under study should be able to reach this level. And this is the search which is ongoing, but we keep looking at. Okay, I think I can stop here, and I thank you very much for the attention. Bye.
Thank you very much, Nicola. That was an interesting talk on all the recent advancement in this field of astroparticle physics and dark matter. That was great. Thank you very much. So there are actually quite a bunch of questions to attend to. First of all, there is an interest in the history of detecting the nature of cosmic rays. So you mentioned that from Earth's observatories, we only see the byproducts because all the particles actually do annihilate as they cross the Earth's atmosphere. So when was it that we were really able to detect the actual cosmic rays? Was that with the Voyager, the instrument on the Voyager spacecraft, or can you tell us a little bit about history of actually detecting the cosmic rays themselves,
yes,
not the byproduct?
I think with the space era, so from the 50s, for sure. From before Voyager, I think that the first spacecraft were Explorer in the US and even other Russian spacecraft. For example, Russian Luna was called, I think, which was also the spacecraft who detected the solar wind in the 50s, also measured cosmic rays. So with the space era from the 50s, we were able to detect the primary cosmic radiation for the first time. Before them, in the 30s, it was already known that cosmic rays were observed at ground were byproducts, were showers. Yes.
Okay, perfect. So it's as old as the space age. And now a little bit about the detection. So AMS is basically a mass spectrometer and determines the mass of the object based on the trajectory that it does. What can you tell us about the other information that we get from that? Is that essentially it, or how could we distinguish between particles with probably the same mass and same charge? Or
yeah, it's actually I don't have here the scheme with me, but it's very complex detector. It's made of several instruments inside, and every instrument make different types of measurement. But what to measure is the charge of the particles at several stages of their trajectories, the energy, the total energy, the velocity, and we call rigidity, means the momentum to charge ratio, and of course with the trajectory we have the arrival direction. With all the information together, for example, the velocity is measured from the time of flight of particles between the top and the bottom of the instrument, but also with another instrument on the bottom called that uses the Cherenkov effect, Cherenkov emission of particles. By combining velocity and energy and rigidity, you can get the mass of the particles. With the charge measurement, you get the charge of the particles. So from mass and charge, in principle, you have the identity of the particle with the nuclear species, or even identify the isotope. It's a matter of precision.
Okay.
The only ambiguity is the sign of the charge, and you need the magnet. I'm saying this because there are many cosmic rays experiments without magnet, and they essentially make all the measurement of AMS, but without distinguishing helium from anti-helium or proton from antiproton, and so they measure just assuming everything is matter.
Thank you. And you also showed us a picture of the periodic table of elements, mentioning that everything has been discovered in cosmic ray. When you say everything, do you really mean, for example, element 118 was also observed in
Good
cosmic
question.
ray?
No, but I mean, there are many, even recently, many measurements, but if I go here, you see at higher element, higher is the mass and smaller is the abundance. And for elements like up to 80, I think, of mass number, they were measured. So means a large part of this periodic table, but the highest, the heaviest elements are not measured, not because they are not there. We don't know actually, but because of their statistic is very low, and usually the experiments don't have a large dynamic range to measure ultra heavy nuclei. There is an American project from Chicago called Super Tiger that is dedicated to measure ultra heavy nuclei. I think they reached, I don't know actually, but I think only the last line of this table is probably still to be measured.
Okay.
But it's matter more of sensitivity.
Perfect. Thank you. And one other thing that was very interesting, you mentioned about how cosmic rays travel. So it's a random walk, they get deflected off all the stuff, and they stay within the galaxy for millions of years. But then you, in the picture you showed, some escape. And also in the types of that you see some of them escape, and then also in the types of cosmic rays, you had 3 types, if I remember correctly, that had different sources. The last one was extragalactic cosmic rays.
Yes.
Yeah, can you talk a little bit about them and how do we detect them? They were ultra high energy.
I haven't commented this. The bulk of cosmic rays is galactic. In fact, I mentioned only galactic particles because the origin is galactic. But if you look at this graph, there are 3 colored areas, and the magenta is those are the most energetic part of the spectrum. Also, where the flux is very rare. Like here means this level means that you have 1 particle per kilometer square per year. So very extremely rare, and so energetic that particles like this actually cannot be confined by the galaxy, because they don't even see the galactic magnetic field. They go straight, so they can be accelerated actually almost everywhere in the local universe. And by the way, the supernova remnants are not believed to be so powerful. There are no galactic accelerator above the PEV energy, the blue band. Not known accelerator. So the origin is probably extragalactic. The best candidates are active galactic nuclei. The process responsible for acceleration is unknown, probably based on the relativistic shocks, but unknown. And that's the extragalactic part of the spectrum. The low energy part, the yellow, is It's still galactic actually, but it's the part of the spectrum where the dynamics of cosmic rays is mostly governed by the solar activity, so by our sun. Doesn't mean that these particles originate from the sun, but when they enter the heliosphere and the solar system, they are much sensitive to solar wind and solar magnetic fields. So their dynamics is mostly ruled by the sun in some sense.
Perfect. Thank you. And now a little bit about antimatter. You mentioned that we observe in the universe very little antimatter. But the question is, given that the only way we know about the distance objects is the photons that we receive from them, and as I understand, there is no difference between the photon created by matter or antimatter. How are we sure that the galaxies outside or far away are not actually antimatter or rich in antimatter?
I'm not into this search. You're of course right. A photon is a photon. But if these photons come from annihilation of like matter and antimatter, like nuclei and antinuclei, like carbon and anticarbon, to fix the idea, they are very well-defined energy. They are monochromatic. So means that if these particles are at rest, carbon is has a known mass of 12 JeV, I think, means that if they annihilate the energy to produce must have 24 JeV, and there is no other source of this energy. I mean, they should emit lines, spectral lines, very easy to be identified, very in principle, but they are not found. So, and there is of course the effect of cosmological redshift and other attenuation, probably, but they should be identifiable. This emission.
Okay, thank you. And now a little bit about dark matter. First of all, there is a question about the news that scientists claim that some of them that they've been able to find some galaxies without dark matter. So can you comment on how does that affect the phenomena you talked about? Because you were talking about how cosmic rays are affected by dark matter, how they interact with dark matter. So if a galaxy does not have dark matter, what about it? How would that change the cosmic rays?
For cosmic rays, I think little effect, because as far as we know now, dark matter is a minor source of cosmic rays. Minor in the sense we don't even know if it is a real source of cosmic rays. So in this galaxy without dark matter, I don't know how. I mean, I don't think that the cosmic radiation trapped in this galaxy is much affected. But of course, a galaxy without dark matter is a very strong, important observation. What when we say without dark matter, I think we should interpret like with an estimated abundance of dark matter below some sensitivity threshold. It's not devoid. I mean, I think there is some dark matter in this galaxy. I don't think it's actually entirely without dark matter. And it's a challenge actually, I think, for the theories and models of galaxy formation, because from these models the dark matter is a very important ingredient. I don't think it's possible to explain the existence of a galaxy, or our galaxy at least, in terms of formation of cosmic structure, without having dark matter. And even in some massive component.
I see. I see. And now there's also an extra question beyond particle physics. Do you expect that galaxies with, as you mentioned, very little dark matter compared to other galaxies, would they have a different shape, or probably, as you said, they would form a little bit differently?
Well, this regarding this discovery, it was not a spiral galaxy. I think it was elliptical and a small one. So I don't know, maybe more similar to a dwarf or galaxy. Or regarding its shape, I don't know. I don't have a right answer.
Okay.
The shape, I can say, but the shape of galaxies, many galaxies are disks, like or spirals, but they have a plane, well identifiable plane. Even it's true that dark matter should be responsible for their formation, even for the shape to a certain level. But the disk is formed thanks to interaction of matter, and in particular to collisions and dissipations. So the disk itself is common, is expected from known interactions of matter. Dark matter, even in our galaxy, which is spiral, dark matter is probably distributed in a spherical symmetry, spherical halo.
I see. Perfect. Let me see. There is another question. So there is another question. The question is not a little bit clear to me. They're asking if all antimatter was annihilated, leaving the small residue of matter that we see as the cosmos that we live in, without any pocket of antimatter. Yeah, so they are they're asking about the origins of this phenomena, that there is lack of symmetry between antimatter and matter. The idea of all the antimatter and that was able to annihilate was annihilated, and what we are left with is just a little bit of matter.
Yeah,
makes it.
That's the idea. But the problem is, antimatter annihilate with matter. If the number of matter and antimatter particle since the beginning is equal, exactly equal, we should not have residual matter. So what should happen to have residual matter and not antimatter? There must be some violation in the interaction, some asymmetry between matter and antimatter at the level of fundamental interaction. Now the question can be, do we know some violation between matter and antimatter at this level? The answer is yes. Yes. There is not exact symmetry in matter and antimatter at the level of weak interaction. It's known. It's known since the 60s from an experiment of Fichte and Cronin, where they discovered the so-called CP violation, which means exactly this. Asymmetry in some interaction between matter and antimatter. So then the other question can be, can this asymmetry just explain this universe as we observed, and explain that the antimatter disappeared? No, actually, we have to understand it, but it seems not enough.
Okay, thank you. So we are at the end of the questions, and people who are wondering about the availability of the recordings of our meetings later on, that depends on the permission we can acquire from the speaker. Dr. Tomasati gracefully agreed to let us publish this talk. So yes, this talk will be available on YouTube, on our website. You could find the link to this on the footer of our website. So before I end this meeting, Nicola, do you have any final comments to make?
I see a question. What's the Pamela project?
Ah, yes.
Pamela is a magnetic spectrometer very similar in the concept to AMS. It's a mostly Italian project, and it's a smaller collaboration than AMS, and it's a smaller detector. It used to be on orbit since 2006 to 2016 in a Russian satellite, and made very important discoveries in this field of cosmic ray physics, like the positron excess. I shown AMS data, but it was firstly reported by Pamela, and it's a very pioneering project, I would say.
Perfect. Thank you very much. So let me remind everybody that you could check the calendar on our website for all our upcoming events at ocastronomers.org. And I would like to thank our speaker again, and thank you all the attendees for joining us, and wish you all great times ahead. Until next month or the next event, you all have great times. Bye-bye now, everybody.